Welcome to AP Chemistry. In this unit, we will discuss all the techniques you will need to visualize chemical structures. This comprises the correct drawing of Lewis structures, assigning hybridization to individual atoms in a molecule, Vesper theory, which refers to electron and molecular geometries, the difference between sigma and pi bonding, and assigning bond and molecular polarity. This video in particular will primarily focus on Lewis structures. However, all of these different techniques must be integrated into a unified, systematic practice. That is, the ideal should be that the student progresses from one skill to the next in logical development. So, let's begin with a word concerning the electronegativity scale, which we will return to a bit later in the second video. Electronegativity is a really nice way of combining both the trends of ionization energy and electron affinity into one table. The takeaway right now for us is that the most electronegative elements are in the second energy level: fluorine, oxygen, then nitrogen. This will be very useful to remember as we begin to draw Lewis structures. Step 1 of drawing correct Lewis structures is to count the total valence electrons first. The charge will indicate whether the substance has gained electrons, when negative, or lost electrons, when positive. This is an incredibly simple step, but it is enormously useful when checking your work throughout. If it has not been indicated, step 2 is to draw the least electronegative atom in the center. There will be many occasions where the skeleton of a structure will be provided to you, but if this has not been indicated, then follow this general rule. Once we know the skeleton of our structure, step 3 is to form sigma bonds. A sigma bond is a direct overlap of orbitals in which two electrons, one from one adjacent atom and the other from the other atom, are somewhat equally shared. It is called a directional or localized covalent bond because valence electrons are being shared, hence the co in covalent, in one location, hence localized or directional. Sigma bonds are the simplest type of such a bond, and since this is a molecule, we will begin bonding with this here. Step 4 is to assign the remaining valence electrons in pairs. Now, in this example, we counted originally 24 valence electrons and placed 3 sigma bonds, or 3 shared pairs of electrons. That leaves us with 18 remaining valence electrons to place. We should preferably complete the more electronegative atoms first. Now, a word on completion. To complete different elements, we should follow certain rules. Hydrogen and helium both follow the duet rule. Their valence electrons occupy the 1s orbital, and since the maximum electrons that it can hold, that 1s can hold, is 2, we will never see more than 2 electrons around hydrogen or helium. Lithium is typically encountered in its ionic form with a +1 charge, so we will not need a rule here. However, both beryllium and boron differ significantly from expectation. Though beryllium is technically a metal, it can be found to form covalent bonds with certain elements. And due to its size and relative weak electric charge, it will follow a quartet rule. That is, it will have a total of 4 electrons around it. Boron, again due to its size and weak electric charge, will follow the sextet rule, having only 6 electrons around it. However, these are the only really notable exceptions. The rest of the elements in the second energy level will follow the octet rule absolutely. That is, a maximum of 8 electrons can fill the second energy level. These elements will never be found to break this rule. After the second energy level, however, there is still a general trend for the remaining elements to have an octet surrounding it. This is because a new energy level is always begun after a p sublevel. That is, after every s and p sublevel of a given energy level, a new energy level is begun. However, bonding cannot occur between differing energy levels. It always occurs with valence electrons in the highest energy level. Therefore, most elements will tend to fulfill the octet rule. However, we should note that third energy level elements and above can break the octet rule. That is, use a d orbital in addition to s and p orbitals for bonding. You should, however, fulfill the octet rule for all of these elements first. Finally, and this is incredibly important, do not add more valence electrons than you actually have. In this example, again, there are only 24 valence electrons in this structure. In completing each oxygen atom using these unshared pairs, we have just run out of electrons, with 8 electrons surrounding each oxygen. However, there are only 6 electrons surrounding the central nitrogen. We cannot simply add more to nitrogen because we want to. This is simply wrong, and it destroys the possibility of doing any further meaningful analysis in the future. Do not do it. Step 5. Now, unfortunately, this slide mixes 2 steps together. The very next step should clearly be to assign formal charge. Now, formal charge is a way to keep track of electron density around the atoms that you have drawn. Here, we need to distinguish between completion versus contribution. Completion refers to following the rules that we have just discussed in the previous slide and counting the total electrons around a given atom. Contribution, however, refers to how many electrons are directly on an atom. That is, how much it's holding or contributing. So, in this case, each oxygen atom will receive a formal charge of negative. This is because oxygen should have contributed 6, due to having 6 valence electrons. However, the structure is showing 7 total electrons directly on it. That is 3 unshared pairs and 1 electron being contributed within the shared pair. Thus, the oxygen atom has quote-unquote gained an electron and is thus assigned a negative charge. The nitrogen atom, having only 3 electrons directly around it, that is, 1 electron in each of the shared pairs it is contributing, is assigned a formal charge of 2 plus, because it had originally contributed 5 valence electrons. Formal charge is incredibly important for chemistry. It allows us to explain the movement of electrons that will occur during our graphing of chemical processes. Make sure you understand this skill thoroughly. Only after the step of assigning formal charges is complete should you do the next part, which is to form pi bonds, the second or third possible covalent bonds. Notice how this is justified by drawing a curved arrow. This must be shown. A curved arrow indicates the flow of electrons, always from a more negative end to a more positive end. A double barbed arrow, which is what you see in this case, indicates the movement of two electrons to the location indicated. A single barbed arrow would indicate the movement of only one electron. Finally, we must redraw the structure, showing the result of our work, as on the next slide. So here we see the final result, as well as having all the possible resonance structures associated with this substance. Note, the nitrogen atom still has a formal charge of +1 in each case. This is because the octet rule must be obeyed for nitrogen, since it is a second energy level element. You cannot simply form another pi bond around it. Also, please note that these resonance structures are not simply additional BS. In order to correctly represent the actual structure, all three are required. This is because electrons do not behave as particles around the nucleus, but as waves. And therefore, our picture of this structure must literally envision all three of these possibilities all occurring at exactly the same time. On the next two slides, I've provided some examples to get initial practice with. You may pause the video and try your hand at some of these. An excellent way to cover multiple forms of information that you'll be required to know is to bring them all together. You absolutely need to be comfortable with knowing both the names, formula, and charge of several notable polyatomic ions. The key to remembering a large number of these is to recognize the pattern provided using the periodic table. Ignoring the second energy level ions, the rest all follow the same pattern of charge as their monoatomic ions. That is, group 17 are all negatively 1 charged. Group 16, -2. Group 15, -3. It is only with the second energy level elements that the pattern quote-unquote resets with oxygen. Next, again ignoring the second energy level elements, most occur in pairs, with the largest pair having 4 oxygen atoms and the smaller having 3. Again, the pattern is different for the second energy level elements, again due to their size, in that the largest has 3 oxygen atoms and the smaller has 2. Finally, the naming convention flows from this. The larger of the two ends in the Latin suffix "ate," which is literally great, and smaller, which stands for the Latin suffix "ite," which can be literally translated as slight. Finally, since group 17 has 4 possible ions, we extend the convention. The really smaller one gets a prefix of hypo, or under, and the really larger gets the prefix per, as in derived from. So for chlorine, we have hypochlorite, that's ClO minus, chlorite, ClO2 minus, chlorate, ClO3, minus, and perchlorate, ClO4 minus. But for sulfur, we have sulfate and sulfite, SO4 2 negative, SO3 2 negative, as well as for nitrogen, just nitrate and nitrite, NO3 negative and NO2 negative. This is different from the naming convention for monoatomic ions, which will always end in "ide," like, say, sulfide, S2 minus. Finally, positively charged polyatomic ions always end in the suffix "ium," as in ammonium or hydronium, shown in the top left. On the next slide, all of the most important polyatomic ions that you will absolutely need to know, with their names and formulas and charges, are provided. The following after that are slides that provide visualization and context for a variety of these, which will feature prominently both in our tests and on the AP exam. The video will resume on the discussion of resonance and resonance hybrids. If you draw the resonance structures for ozone correctly, you will discover two resonance structures that will both have a positive charge on the central oxygen. This is similar to how nitrate ion was drawn, in which a positive charge always remains on the central nitrogen. This coincides with its electrostatic potential map, shown to the right, which indicates an overall positive electric charge with blue and a negative electric charge with red. This as well connects to its actual chemical properties. Thus, when a substance is not participating in a chemical process, when the substance exists undisturbed, an average of the structure, a resonance hybrid, can be drawn to most accurately represent that substance. This is simply drawn by showing everything consistently the same in each resonance structure, and then drawing a partial charge where formal charges have been resonating. In this case, since the total resonating charge is 2 minus, and the charge has been distributed over 3 oxygens, the partial charge on each oxygen is 2/3 minus. If we return, however, to the case of nitrate ion, we realize in comparing the two structures that carbonate ion is much more stable than that of nitrate due to a more even distribution of charge. Thus, correctly drawn Lewis structures can help indicate and explain chemical properties. This is the reason why explosives are commonly peppered with nitro groups, NO2 groups, while carboxylates, CO2 with a negative charge groups, are commonly associated with fats. The essential takeaways for the first part of this unit in this video are as follows. Be able to complete accurate Lewis structures, as well as be familiar with all the essential polyatomic ions. Till next time when we consider the mysteries of the absolute, Crit.